When we think about safety in really critical systems, I'm talking airplanes, nuclear power plants, things like that, we're putting all our trust in testing to catch problems before they become, well, catastrophes. But what if the very way we test is fundamentally flawed? Okay, let's dive into this because it's a fascinating look at the hidden dangers of using really small amounts of data.
And really, this is the question at the heart of it all. We're not looking for some giant obvious crack. We're talking about microscopic flaws, totally invisible to the naked eye, that can grow under stress and lead to, catastrophic failure. Finding these is a huge, huge technological challenge.
Right, so there's an entire field of science dedicated to this. It's all about finding those tiny, hidden defects in super important components before they can fail. The stakes just couldn't be any higher, so the technology has to be incredibly precise.
And the main tool for the job is something called non-destructive evaluation, or NDE. The easiest way to think about it is like a medical ultrasound or an X-ray, but for a machine part. It's a way to look inside a material for damage without having to cut it open or break it. It's basically the science of seeing the invisible.
Now, here is where things get really tricky. I mean, in a perfect world, we'd just scan every single square millimeter of every component. But in reality, NDE testing can be unbelievably expensive and take a ton of time, so we can't test everything. We have to rely on samples. And that leads to a really big problem.
And when I say small, I mean really small. This is what's so wild. The source material points out that we might be making literal life-or-death decisions based on as few as 6 to 30 data points. That's just a tiny, tiny window into the overall health of a massive, complex system.
So in an ideal world, we'd have a ton of data, right? We'd get this nice, clear, reliable picture of an object's condition. But the reality we often face is completely different. A small, random sample might not be representative at all. It could be totally biased. Maybe it accidentally shows us only the good parts, and that gives us a false and, frankly, very dangerous sense of security.
So what does this danger actually look like in practice? Well, the source material gives us this brilliant illustration that gets right to the heart of the problem. Let's call it a tale of two curves. Okay, check this out, because this visualizes the lie a small sample can tell so perfectly. That dotted line you see, that represents our tiny sample of just 6 data points. Now, based on that sample, we draw one conclusion. But the solid black line, that's the population. That's the true state of the entire component. And as you can see, they don't quite match up, which has some pretty scary consequences.
And here's where it gets really dangerous. Based on our small sample, that dotted line, we would set our detection threshold thinking we have a 90% chance of catching a flaw. We'd build our whole safety protocol around that number. But the reality, the solid line, it shows that the very same setting actually gives us a 96.2% detection rate. What does that mean? It means our sample was biased. It gave us a completely wrong idea about our test's real capability. We've built our entire safety case on bad data. This miscalibration could lead us to wrongly certify a component as safe, all because we misunderstood how our own test performs.
Our researchers knew this was a massive risk. Just grabbing a few random data points and, hoping for the best, that just wasn't going to cut it when lives are on the line. So they started a systematic search for a smarter, more reliable way to gather this data.
And here's the absolute key to it all. In the real world, we don't get to see that solid black line from the chart. That's the whole reason we're sampling in the first place, because the true population of flaws is unknown. So just picking data points randomly is a total gamble, and we have no way of knowing if our little sample is a good one or a dangerously misleading one.
So to find a better way, researchers basically set up a bake-off. They used simulations to test a whole bunch of different sampling strategies against each other. They compared standard random sampling to other, more thought-out methods to see which one could give them the most trustworthy picture without needing thousands of data points. And out of all this research, a clear winner emerged. It was a method that wasn't about collecting more data, but about collecting smarter data. Turns out it's a pretty well-known technique in statistics, and it proved to be the key. It's called stratified sampling, and the idea is actually really simple but so powerful. Instead of treating the whole object as one big unknown blob, you first divide it into logical subgroups, or strata. You know how a political pollster doesn't just call random phone numbers? They make sure to poll different age groups, different income levels, different locations, all to get a true picture of the electorate. It's the exact same principle. So here's how it works. First, you identify those distinct groups. Maybe it's different types of materials or areas on a component that are under high stress versus low stress. Then, second, you take a small, random sample from within each of those groups. And finally, you combine those many samples together. What you get is a small data set that acts like a miniature but really accurate model of the whole thing. And the benefits are just huge. This method seriously improves the accuracy of your estimate without needing any more data. It lets you focus on the most important areas, it reduces those wild swings in results you can get from a bad random sample, and, most importantly, it creates a sample that is truly representative of the whole.
Okay, so let's bring this all together. What is the big lesson from all this research? Why does this deep dive into statistical methods matter so much in the real world?
Well, the source material itself puts it perfectly. It's not about luck, and it's not even about getting a bigger sample. It's about designing your data collection process with some thought. A representative sample is simply the most reliable way to get results you can actually, truly trust.
And that's really the key takeaway here. It's quality over quantity. A small, intelligently collected data set using a method like stratified sampling is going to beat a much larger but purely random data set every single time. How you gather your information can be way more important than how much of it you have.
And that leaves us with this final, kind of provocative question to think about. When we are dealing with systems where failure is simply not an option, is leaving our analysis to the luck of a random draw ever an acceptable risk? After looking at this, the answer seems pretty clear, doesn't it?